last week, but I guess Noga did a very good job starting the course. But officially, this is the first lecture, and the first thing I want you to know that I start on time. The second is really I want you to tell me something about yourself. I mean, who exactly is sitting here? What is in the background of everyone? Because we need to somehow, this is going to be a complicated job to really bridge between the different levels of knowledge that we have in this class. Then I want to talk a little bit about the structure of the course and the goals and requirements and skills needed and what we actually want you to get out of this course. And so first of all, who are you? I mean, how many here are LSEC or ICNC students? Okay, quite most of you. So these are first, second, third year. How do you distribute? How many are first year? Okay. What is your background? Those who are first year? Okay, I just want to make sure that you have the minimal requirements as far as mathematical background. We'll talk about it in a second. Otherwise, we actually recommend this course for second year. But if you're coming from natural sciences at large, I mean, actually I prefer computer science, physics, or mathematics, maybe engineering. Those I know have the right background. The others may need some sort of buffer between me and the first degree. And we actually supply this introductory course to mathematics to others, which I really urge you to take if you feel like the need to do this. Okay, how many are second year? Okay, this is a mandatory course for you. And how many are third year ICNC or one? Only one. How many here actually took the course already and need to do it again? Oh, you don't have to tell me, but I know there's some here. Okay, you ask me about it. Okay, I'll say a few words about it. I guess the other people who are actually taking the course are not here. Okay, how many are non-LSEC students? Okay, well, so you're mostly computer science, or how many are computer science students? At what level? I mean, third year or more? Master, okay. How many are less than third year students in computer science or physics or anything? None. How many of you never had a course in probability theory? It's not a serious course, I mean. A mathematical course in probability theory. Okay, so all of you had some background in probability. This is very good. How many of you think that they know everything in this course? They don't need to be here. No, really, I mean, I know there are people like this. Every year I get some requests to show me that they learned everything and don't need to come anymore. Okay, and nobody dare to say it right now. Okay. How many need the course to be in English? One. Okay. No, good. Actually, ask your other friends to come as well. I mean, we'll do it just for you, but it's enough. I mean, actually, the course is officially given to LSEC students who officially promise to have the mandatory courses and all the courses in English. So we'll make every effort. And I know it's going to be hard for some of you, including me, but we'll do that. Okay, to actually give the course in English. But maybe from time to time we'll see something in Hebrew to make things a little clearer. Okay. So it's more or less the kind of audience I expect to see here. Sometimes we even have more physicists or more computer scientists or more engineering students. I mean, actually, you know, this course has a long history. We started the computational neuroscience program, as some of you may know, before I guess some of you were born. I mean, something like the first time I taught this course was 1993. You know, this was when Rabin was still alive, and we had big hopes for peace, and Jerusalem was much nicer, and we actually believed that we are going to understand the brain. I mean, there was a lot of optimism. It's actually quite amazing. I mean, most of the material for this course was really prepared in the 80s, when some of us, including me, thought about having a course in computation, that there's some need to do a quantitative computational course for neuroscientists or for people who want to understand the brain. This was, as you may know, I mean, the big revolution, as you might call it, the neuroscience, the computational neuroscience revolution really started somewhere in the 80s, between, let's say, 82, where the Hopfield model and appeared together, let's say, with the first theoretical papers on learning theory, like the papers of Valiant and others, and which eventually raised a lot of hype during the 80s with everything we now call the connectionist revolution. I mean, the belief that neural networks, or the concept of neural networks, can actually help us solving all the problems, all the problems that we, in computer science, we then used to call AI, or artificial intelligence problem. I mean, how to mimic human cognitive functions with computers. And at the same time, this concept of neural networks, which was very hot at the time, was thought to give us some deep understanding and insight on how our brain works. So this was really, it really started, I think, very clearly in the early 80s. Actually, you can see that some of this is based on work and ideas that came much earlier in the 60s. And there was the first wave of neural networks, if you want, came actually at the end of the 50s and beginning of the 60s with the idea of the perceptron, Rosenblatt, Marvin Minsky, maybe you know some of these. So actually the 60s was really the first hype of neural networks. Then it died out for some historical reasons which are really interesting. I mean, people actually proved, this was, for example, the famous book of Marvin and Minsky on perceptrons, some of you have seen probably, really showed that neural network cannot work, or that perceptron is a very bad idea. And they were so convincing that essentially they killed the field for about 10, 12 years, from the mid-60s till the beginning of the 80s. Then it came back again, and it actually came back from new ideas about how to do pattern recognition, how to do vision, computer vision, how to do speech recognition, and things like this. That at the time, the technology was almost ready for the beginning of work on these things. Actually, a lot of the progress in understanding how to deal with complex signals came from the telephone companies, Bell Telephone at the time, trying to build, to work on speech, both synthesis and analysis of speech. And later on, I mean, speech recognition eventually was not the ultimate goal, but it took many, many more years until it became more or less a reality. I'm just telling it to you because for all of you, it's an ancient history, but I actually lived through this time. It was quite exciting. And yes?
It sounds like the theoretical background came much earlier than the practical implementation.
No, I think they went together. I mean, actually, the drive for the theory was the practical implementation. I mean, the need to do, for example, speech coding, or the need to do classification of images, or the need to do what we now call pattern recognition in general. I mean, how do you? It started actually like many other good things that came out. The bad thing that's called the Second World War. So actually, a lot of this revolution really started during the war. I mean, where people started to work on aerial photographs, and people started to work on communication, on cryptography, and many other things that came out of the war effort, really, including many of the topics of this course, like information theory, like statistical decision theory, and many other things, including things I'm going to talk about in the next hours, like sequential decision theory, and all these things came out of the war effort. It's amazing. I mean, actually, it's really sad to say, but the war really pushed essentially the technology of information science, essentially invented it, created it. We can really say that both the theory of computation, the concept of the computer, the concept of an algorithm, and everything that we now call the age of information on one hand, and the work of the work of Turing, and that follows the work of Gödel and the work of many others in the understanding of computation, was eventually crystallized during the war. Again, around the effort of breaking codes and things like this. And at the other side of the ocean, I mean, not in England, but in the US, the mathematical theory of information was developed as an effort to understand what are the limitations on transmitting information from one point to another point by Shannon and others at Bell Labs. And so these are really the foundation. Of course, statistics and the probability theory is much older, but it's not much older, actually, surprisingly. I mean, actually, probability theory really became part of legitimate science in some sense. I mean, mathematicians started to take it seriously only at the beginning of the 20th century, maybe 19th century. Actually, the first serious mathematician who actually did something serious about probability was Laplace, who wrote his famous book about probabilistic inference. It was really the first attempt to write a mathematical theory of probability. Before Laplace, these things were considered, you know, the business of gamblers and all sorts of non-serious professions. How to bet in cards, how to calculate the odds in horse races, who knows what. I mean, all the things that respectable people don't do, like breaking codes and so on. But in a sense, it took almost 2,000 years since the beginning of what we call logical inference, which is largely attributed to Aristotle, the beginning of logic, to the idea that we actually need to deal with uncertainties in some rigorous way, and the invention of probabilities. I'll say something more about it in a few minutes. So, and actually, it really became a legitimate part of mathematics only after some axiomatization really put it on a solid axiomatic basis, which really happened only in the 20th century by people like Kolmogorov and a few others who were trying to formalize it. Actually, mathematical statistics appear a bit earlier, but it's a 20th century science. What is interesting is that it's, in some sense, not unique, and I'll say a few words about this historical part also. Just a second. But before we go into the history of the field, I mean, so as I told you, I mean, so the course itself we started to think about it in the 80s, and the idea, I was facing this problem, what is the minimum requirement for a computational neuroscience program in terms of understanding something about computation, understanding something about quantitative inference, as we call it, I mean, hasakah kamutit, or something like thinking about how to translate a problem into formal mathematical statement that we can actually prove something about. And this is, I think, is essential. It's one of the main goals of this course, is to train you in quantitative modeling and analysis. But on top of it, I mean, so that there are many concepts that came from many different directions. As I mentioned, I mean, some of them come from engineering. They need to think about communication. They need to think about data compression. They need to think about pattern recognition. I mean, these are all considered this engineering, practical problems. At the same time, there were really basic, fundamental, almost philosophical, or really philosophical questions like, what do we mean by uncertainty? What do we mean by randomness? And can we deal with it? How is it related to the idea of computation? I mean, all these things are somewhere in the background of whatever we say here. And then on top of it, I mean, there were also all those sociological, cultural issues that are always in the background. I mean, you can't ignore them. We're talking about human beings. So, you know, statisticians, for example, didn't believe in information theory until very recently, for some reason, because this came from engineering, from the war effort. Statisticians are pure idealists who don't deal with dirty things like cryptography, let's say. So it really came very late. If you look for example, a course in information theory and statistics, you will not find one. not only here, in most places in the world, until really recently, maybe the last 5-10 years. Statisticians actually started to talk about information in the sense that we talk about it. Actually, statisticians even ignore the. There's my phone somewhere. Obviously, we're going to. Statisticians even ignore the notion of computation until very recently. Doubt? Okay, tell me when this happens, because then it means that the recording is bad. You hear me now? Okay. So again, computation is another almost orthogonal line of thought that came out of logic, as you know. Some of you know, I hope. Actually had a lot of bad feelings about uncertainties in statistics. Actually, it's amazing, again, to say that. But when I came to the university in 1992 or 1, and suggested to have a course in statistical methods for computer scientists, which eventually became machine learning, and is now a very central domain in computer science, as you all know, I hope. At that time, 1991, serious people in computer science like Michael Rabin and others told me that this is not, that it doesn't belong to computer science. I mean, it should be taught in physics or in engineering, but not in computer science. So computer scientists were so solidly based on logic and what we now call rule-based systems and things like this, that it was really hard for computer scientists to accept the fact that statistics play a role in understanding computation, and that actually there's a synergetic, as we call it now, combination. I mean, if we actually add statistics to algorithms, you get a lot of new power. So it's only, we're talking about 20-something, maybe 20-something years. Yeah, it's not much more than that. And actually, we were the first, in Israel at least, to teach machine learning. This was, at the time, this course was the introduction to machine learning and computational neuroscience in some sense, and they merged it together. Anyway, to make a long story short, it's actually very interesting, this history, because it tells you how people have misconceptions and mistakes about ideas and what is important, what is not important, even very good people. But so I taught this course between 93 and 2008. And then I said, okay, that's enough. And my very good student and colleague now, Amir Gloverson, took this in 2009, as far as I remember, and taught it in the last few years, more or less on the same old lecture notes that we had, that I put together more or less in the early 90s, which what I thought is important. Okay, now he is on sabbatical, as you know. You hope only for 1 year, so he asked me to teach it again. Okay, so I must say I looked at the notes of the course, and many of them I know exactly where they came from and how arbitrary they are. And said, okay, it's actually not so bad. In some sense, despite everything that happens in the last 20-something years, some of the basic things that we taught in this course were correct. I mean, they're still valid. Actually, you must understand that the whole field of neural networks, let's say, call it at large, I mean, this revolution of the 80s, the hype that came from the works of Hopfield and perceptrons and all that, essentially died out. I mean, there was a long period between, let's say, 95 and the last few years, where people, especially in computer science, thought that this is a bad idea. I mean, and we should do learning on some rigorous, foundations, and invented actually a lot of interesting tools. Some of you may have heard about them, like support vector machines, kernel techniques, all sorts of rigorous analysis of what we call PAC learning, and many other things. Some of them are still here and still very important, are provably learning algorithms. Actually, the problem of learning really became central to this issue. This was more or less the first thing we start to understand rigorously. What do we mean by learning? Actually, So when we wrote this, it was really more in the spirit of neural networks in the background, but I thought that, okay, you know, there are some foundations, there are some things that are really important, like understanding probabilistic thinking, understanding statistical inference, what you call in Hebrew statistics, to understand decision-making under uncertainties, to understand not only learning, but some aspects of what we now call cognition or behavior in general. And learning is only one part of the story. And actually, now we know it's really not only one part. It's part of a much larger domain, which includes everything that we call cognition. Yeah. So learning is one of them. Memory is one of them, which was, again, one of those early things. What do we remember? What we should remember, and so on. Behavior. I mean, how do we make decisions? How do we act? How do we plan? What are the things that we need to remember in order to act in a useful way, and so on? What are the fundamental limitations, physical or computational or others, that prevent us from, allow us to learn, or that prevent us from learning? So these were all the kind of things that we thought are important, and essentially this is why the course looks the way it is. Okay, but then we faced, of course, another very big problem, is that the students of this course, you for that matter, and have very different backgrounds. So we couldn't really have a course that really covers it, let's say, at the level that I would like to hear it today. But at the same time, so there are people here who never really did quantitative thinking in terms of probability theory, let's say. On the other hand, there are physicists or mathematicians here that think they know everything. And we couldn't really, I couldn't really allow myself to lose any of these. So the course has built in it essentially several different levels in which so some of you may hear those things for the first time in their life and have hard time just understanding the very basic concept. That's fine. But I hope they will get out of it this very basic quantitative thinking. Some of you who think that they know everything will actually discover here some very deep, in my opinion at least, the connections between things that they never thought are connected. And actually, I will try, and it will make the course much more difficult, both for you and for me, all the time to talk in these different levels. I mean, to say something to those who hear it for the first time, and to still be challenging and interesting for those who think they know everything. At least what I always say, and it sounds a bit funny, but I like to learn from every lecture that I give myself. And I usually do. I mean, discover something new for me. And this is, of course, not very easy for students sometimes. But during the lecture, I discover something that I never thought about. But it makes the course a lot more challenging and interesting, I think, if you are willing to be with me. So in principle, I always like to say that there are no overqualified students for this course. But at the same time, of course, people who took it already or really believe that they're way beyond these trivial things. As far as I'm concerned, this is a graduate course. I mean, you are all the grown-ups. You are PhD or master students. I mean, you know what it means to take a course. You know what it means to learn seriously something. If you don't want to do it, it's your problem. What I can tell you is that it will be very difficult to pass the exam without actually going through the exercise seriously, to try to do them yourself, all of them. And so I got all sorts of questions. Can we submit it in pairs or triplets or quadruplets? I don't know how many. Or can we skip one, do one and not the other? All sorts of funny questions like this. Not me, and certainly not Noga. I'm not going to be policeman to anyone here. If you don't want to work, don't work. It's no problem. I am here to educate or to challenge you or to give you what I think are important ideas in the best possible way I can, which, of course, always can be improved. And you are here to take whatever you can or want out of it. But the formal requirements of the course is that you take it seriously, attend the lectures, do the exercises, and do even more. I mean, I actually want to get to see here people who really are interested in the extra and bonus things that we're going to give you to go beyond the course, especially those who really know many of the elementary things. All right, so as I said, I'm going to modify the course because I know that things have changed a little bit. And so, but the basis is still, to some extent, or to a large extent, this old and very poor book that two of my students, Gal and Lidror, who were TAs here, wrote back in the 90s, still around, the Hebrew book. And there is actually very nice lecture notes in English that Amir Gloverson prepared, which are still very carefully following essentially the same outline with a few additions and omissions of the original course. And of course, all the learning theory part that is not included at all in the Hebrew lecture notes are covered to some extent by Amir lecture notes. But of course, these are all lecture notes in the sense that it's not a very organized, what we call textbook, and there are many textbooks. The problem with textbooks is that none of them really covers the material of this course. I mean, it's taken from many different places, and therefore, really to understand what's going on here, you need to see how I connect, we connect the different concepts. But as you can see, there are some good books. So first of all, probability and statistics is really the bread and butter that we need to understand. I'll say something about this in a second. Sorry. I don't get any phone call unless I start speaking in a lecture. Okay. So all these tools, I mean, probability and statistics, for which there are many, many books. The book that actually Amir recommended is the book of Maurice de Groot, but there are many others. Or any good book on mathematical statistics has cover essentially all the foundations of what we talk about here. But as I said, statisticians, for example, ignore completely the notion of information, which is very fundamental to what I'm going to do. So I'm actually going to introduce concepts of information theory right at the very beginning of the course. And actually, information theory, in my view, is closely linked with statistical physics, something which is, again, another discipline, which for some of you may be completely alien, and from others, those who take, let's say, the courses of the LSEC, I mean, or those who came from physics, it's actually maybe even the more intuitive thing. So, for example, I'll talk here about the thermodynamic meaning of information, something you hardly find in any textbook. Or I'll talk about the cost of information in terms of energy, the metabolic cost. I'll talk about things like the connection between fundamental theorems, coding theorems of Shannon. We'll talk about them at some point, and the analogous pictures in statistical physics, because I really believe that in order to understand the brain, for example, we really need to bridge between these different languages. We have to have some ideas about how physicists think about it, and how engineers think about it, and how mathematicians think about it, and why is it so important to do it together. So again, going to textbooks, there are many, many good books on pattern recognition and machine learning. We recommend here, for example, the book of Christoph Bischoff. Christopher Bischoff, it's a textbook in the sense that it's really not trying to do too many original things, but it covers. Actually, there's an older book of Duda and Hart on classification. All these things, by the way, are written or are going to be written in the web page, so you don't have to remember it now. And then, so Duda and Hart and Bischoff, and then of course we're going to talk about information theory, and then essentially one good textbook, which is the book of Kover and Thomas. We'll talk about this later. And then in the third part of the course, we actually try to take these concepts. Some of them are very non-intuitive and very hard to understand initially, and bridge them and take them to this last revolution, the last phase of what we call formal or mathematical learning theory. It's again only in some very superficial and preliminary way. The reason I do it now because there are many other courses luckily for us, at the Hebrew University on learning theory. In particular, we have a mandatory course for computer science, which is called machine learning or introduction to machine learning or something like this, which is a good course, at least when it was taught by Shai, and before that others, Yoram and others, and some years, or maybe even this year, by Amnon Shashua. But so that's a different course. It's a different course, but it's closely related to this one. And I strongly recommend the computer scientists who want to learn about learning to take it. How many actually took it here? Okay, quite a few. Okay, so that's good. So I'm not going to cover. I'm not even going to compete with this course. I'm going to use it in a different context. And I want to give all the others some ideas about what they mean by formal learning theory. And as I said, learning to me is just part of the problem. It is related also to control, to planning, to behavior, to many other things which are not covered under the name learning theory, which I believe are really, really important. Okay, so it's a very ambitious course. Obviously, we can't do everything in just 4 hours a week.
Question.
Yes.
Can you clarify, so how much will the course follow the book, and how much will the book follow the course?
Look, as the first approximation, the book covers about 1/2 of the course. More or less, maybe a little more. The first part, more or less. There are going to be several extensions to this, which I'm going to point out exactly what I mean by that. And they are all of learning theory is essentially not mentioned here. So it's more than 1/2, maybe. You'll see a lot of, the beginning is very similar. But as I said, there are extensions, and I'll try, although it's much harder for me to do it, to actually add things to Amir's lecture notes. I did it for the first lecture, more or less. We'll put it on the webpage. So essentially, whenever I say something which is not covered, we'll try to do it in English in the notes, and you'll get it more or less. And of course, with what Noga has done already, I mean, giving you more or less write-ups of the exercises, which are amazingly important. I mean, this is the most important part. This is where you actually get to do things with it and understand it. There's no way of understanding this concept without an exercise, without a recitation as required. So this is essential. It's actually more important than the lecture as far as I'm concerned. That's about it. I mean, all the other things Noga already told you about the requirements of the course and so on. But I want it to be fun for all of us. That's the most important thing. Really enjoy. Okay, questions? All right. So I now formally started, and you already talked about probability theory with Noga. And the first question I want to ask is why probability? Probability, calculus or theory or inference, whatever you want. Okay, I'm sorry if my handwriting is really terrible, but I hardly can write. Just doing my best, it's all right. So it's why? So why do I ask this stupid question? So you all know something about probabilities, and probabilities really are going to be the foundations of all this big tower that I'm going to build on top of it. So you really have to be absolutely certain that it makes sense, that it's correct, that there are no logical holes or missing components in this theory. And so all of you, including what Noga did last week, just gave it to you. Here it is. Okay, these are probabilities. There's sample space. There are events. There are several properties of calculus. I mean, which I'll mention in a second. And that's it. Take it or leave it. God-given. Is it really the case? So what do we really want to do? I mean, we want to somehow do an inference under uncertainties. We really want to deal with uncertainties in some systematic, correct way. So, for example, is there a single probability theory? I mean, maybe there are many others. I mean, who said that we have to work with this particular action? Okay, so this is actually, again, it's bordering the philosophy of science question, but actually mathematicians are thinking about it very seriously. Can there be other probability theories? I don't want, we can teach actually a full course only on this question. I mean, what is the foundation of probability theory? I just want to know that this is a serious question. And if you ask you, what would we like to extend? What are the things that we want to start with? To actually take for granted as true. What is it? So I actually said it in my introduction. I mean, it all starts from what we call logic. Now, logic is a very ancient endowment. I mean, this is something people have invested a lot of thinking since, as I said, the Greek. Aristotle, as I said, one of his main achievements is really the first formulation of what we call logic, or logical thinking. It first of all stands very deeply rooted in our language. I mean, language, to some extent, the way we speak, is in a way and built on some sort of logical proposition calculus. I mean, on the fact that there are things that are true and there are things that are false, and that's it. I mean, so logic essentially tells us that there are what we call propositions, statements like today is Wednesday. Okay, this is a statement. It is either true or false, or it's raining outside. Okay, it's true or false. I mean, essentially, so this idea that things can be either true or false, and that we can infer one proposition from another proposition, what we call an argument, a logical argument. And the logical argument is a set of sequences, a set of propositions like this. That if, for example, all birds are pink, and I am a bird, then I am pink. Now, none of these are true statements, but the argument is valid. Okay? Because so an argument can be valid. An argument is a consequent set of arguments, what we call propositional calculus. I mean, how do we infer one proposition from another proposition? This is the business of logic. Okay, and this was done very successfully. So a valid argument can be made out of two propositions, and false propositions doesn't matter. And it can be an invalid argument if my deduction, my set of inference, inferring one statement, one proposition from another one is wrong. There's something flawed in the validity of the argument. Then we say it's a wrong argument, it's a false argument. Okay, so there's some deep connection. Of course, many of you learn logic much more seriously than that. And you know that this is actually the basic of what we call computation, an algorithm, a statement about the world, and so on. So what we took for granted here is there's logic, so there are propositions which can be true, denoted by T, or false. And this was the state of affairs for many, many years. It's amazingly until more or less, as I said, the 18th century. Actually, not exactly. In the Middle Ages, people already started to think about gambling, and in the Middle Ages, in the Renaissance, there were many early attempts to. I mean, what sounds completely obvious to us now, that this is incomplete. Logic itself, there are statements in the world which are neither true nor false, or at least we don't know. Okay? So the world is not black and white. There's some level of certainty that we would like to extend from these true and false statements to allow us to extend logic, really, in a consistent way. What do I mean in a consistent way? So we wanted to include logic in a sense that if we are really talking about true and false statements, all the propositional calculus of logic will still be valid. But at the same time, we want to think about statements, events, probability, propositions, if you want, that are not necessarily true or false. Also, okay, what would we like to do? So we want to assign to an event, which at this point I just write like something like this. What we mean by event or a proposition, we want to assign a number in a way that will have these two limits of true or false as, let's say, 0 and 1, or false and true. And something in between will tell us, okay, what is our level of certainty or level of belief in the correctness of this statement. So the idea was really to extend logic to something which we today call probabilities of an event. A is an event for that matter. And now you can ask many questions on how to do this. What are really the minimal assumptions, the minimal actions that we need to put on this extension? And this was actually done. I'm not going to do it here, though I really like this line of thought. What are really the minimum requirements? So, for example, we want to assign a real number between 0 and 1 to an event. Okay, that makes sense, because it really extends if we think about falses as 0, 1, just these two sets. It's true if it's 1. This is nothing but assigning numbers to this statement true and false. So we want to extend it to a measure between 0 and 1, such that it will be, if it's 0, it will really be false and would remain false, and if it's 1, it remain true. Okay? This is, okay, but this is not enough. There are two fundamental axioms in probability theory that Noga actually mentioned very, very quickly, that you can question. I mean, you can ask if we really want to, we need to have them. So what are these two axioms? I mean, essentially, so okay, so you want to assign a number between 0 and 1 to every event. This, of course, there are many things like this. So the intuition was that we have a picture like this in mind. There's something which we call the sample space, and I'll talk in a minute what do I mean by this sample. Sample is another new concept, very, very different from everything I said so far. So this sample, let's call it omega. It's a set. So the idea was really an idea of set theory, and events are subsets. Let's say A can be a subset of this large space. And now I have to ask myself in terms of sets. What do I mean by the probability of A, such that it will be consistent with logic? So essentially, I may think of two events, let's say. So both A and B are some subsets of omega. And so I go back essentially what logicians did to logic, which is building it on top of set theory at some point, and what probabilistic did to probability theory, building it on top of set theory again. And then, so now I'm making all sorts of assumptions. For example, that these two sets, A and B, these two subsets, are measurable. Okay. How many of you heard this? What I mean by measurable, the fact that actually assign a function, a number, P of A, which should take me from this subsets of omega. So it's not all of all. In principle, I would like all the possible subsets of omega, 2 to the omega. You know what it is? You know this notation? How many never saw it before? Okay, 2 to the omega is just the set of all subsets, okay? At this point, I'm not too formal, but just a little bit. So 2 to the omega, essentially, if this is a finite set, let's say the number 1 to 6, integers 1 to 6, 2 to the set is all the subsets of this group, and there are 2 to the 6 such subsets, which you can easily prove to yourself. Okay, so I just map it into 0, 1. But then I'm asking something more than that. I want some consistency with logic, so I want that the limit of probability go to 1 and probability go to 0 will be consistent with everything I know about logical propositions. So this is essentially the exercise that some people did, and I actually recommend very much a paper which I like of a guy named Cox from 1942, I think, again during the war, who actually did it in some very nice and more or less easy to follow way, although not fully general, because he assumes all sorts of things like differentiability and many other things. But in principle, you can derive this by some sort of an axiomatic approach. And what is really the requirement that come out of it? So you actually ask the following logic, what should I mean by two things? So what I want, this combination of measurable sets to be closed under 2 or 3, actually very important set theoretic extensions of the basic operations of logic. So what are the basic operations of logic? Or, and not. Okay. So this you all should know. So logic is made of propositions, which are eventually made out of combination of things like, and from that I can actually generate, actually I don't even need all of them. And the not are enough, but I can, for these three things, or and of not, I can generate essentially every logical proposition. So these are the operation of logic. In terms of set theory, what does it mean? So what is the OR of two sets? It's the union. Okay. So OR goes to A union B. Okay. AND goes to what? And goes to A intersection with B, A and B. And not goes to what? The complement. Yeah. So not goes to the complement, or the omega minus A as a set. Everything that is not in A. Okay? The complement of A. So there is a very nice map between logical operations and properties of sets. And now I want my sample space to be closed under as many as I can operations like this. So I want all the unions of subsets to be there, and all the intersections of subsets to be there, and all the knots or the complements of subsets to be there. And this is what I call sigma algebra, but never mind that. So I have all the possible subgroups, but just for those mathematicians here, I see some. It's actually a bit disturbing, but it's inevitable that when we talk about something like the square here on the board, let's say the unit square, not all the subsets are in this class of intersections or unions of countable intersections of union and complements. Not everything can be. There are non-measurable sets. That's all I want to say about it. Just remember that. But in this intuitive picture, a nice kind of measure is the area of the subset. Okay. So this is, let's say, the unit square. So this, a nice natural measure, is an intuitive way to think about probabilities in this case, is the area of a set. So the area of the whole cubic square is how much? I just want to see if you are awake. Is 1. Okay, so I have this first axiom, the probability of omega is 1, and the probability of this is the probability of the complement of omega, which is what? It's the null set in this case. There's nothing there. Okay, so the probability of the empty set is 0. And now it starts to, this is essentially logic, okay? Now it starts to be interesting. I want to extend it beyond logic, and I'm finishing in 2 minutes, don't worry. This is first class. So I want to be able to say something about this and about this. Okay? Once I say that, and I already say here, and about this, and about the probability of the complement. Once I say that, I have all the axioms. I just have to extend it to countable number of intersections and countable number of unions. And then I have essentially what we call the calculus probabilities. That's it. So again, I'm stating this question again. Is it unique? I'm going to have an expressions for this in terms of numbers, in terms of calculus. What is the probability of a union? What is the probability of the intersection? From that, I'm going to deduce the probability of the conditional event and all that. But again, what I have in mind is this intuitive picture. Always think about areas here. And once you think about areas here, you essentially know what should be here. And again, the question is it unique? So the answer is yes. In a sense, there's only one way of extending logic to these numbers between 0 and 1, which will be a true extension of propositional logic when we talk about a certain event, so 0 and 1, but will be consistent otherwise with this fundamental axiom. And this is exactly what we now call probability theory. But there's a very interesting caveat here. It's not the only possible extension. And so there's something else here. I'm just saying this is one of those statements which may be completely ignored by those who hear it for the first time, but just to challenge the others. If I don't ask my numbers to be real between 0 and 1. Let's say I want to map them to complex numbers. Why? Because why not? Okay, I can assign complex number to events. What's wrong with that? So it turns out that, again, the two axioms that follow the two rules that appear here, I mean, the probability of a union is the sum if they are disjoint, and the probability of an intersection is the product if they're independent. This is essentially what I mean by the axioms. So disjoint set probability goes to sums. Independent set probability goes to product. That's all you need. If I see that these two things must be obeyed even if these are complex numbers. The fact that these are real numbers is not at all obvious. And if I omit this axiom, the big surprise is that you get, again, a unique extension. And this unique extension, you can call it complex belief system, or complex inference, or complex probabilities, or whatever you want to call it. We don't call them probabilities, not to confuse ourselves. But who knows what it is? What is it equivalent to? What do you think? Any guesses from the physicists here? Absolutely. So it turns out that if the only possible extension, which if you omit this notion of real numbers, you get quantum, what we call sometimes quantum logic or quantum mechanics. So this is actually quite interesting. So I could forget about probabilities, decide that I work with complex numbers, and get out of it something which turned out to be the real theory of the world. I mean, quantum theory is not just craziness of some physicists, at least the way we understand it now. It's what really underlies the world. There's no classical world and quantum world. There's quantum world and some approximations of it or some limits of it, which we sometimes call the classical world. But the world is quantum mechanical, fundamentally, at least according to what we believe now. And it's really fascinating to know that you can get to quantum mechanics directly from logic. For quantum mechanical amplitudes, as we call them, these complex numbers, sum for disjoint events and multiply for independent events, exactly like probabilities. And then, of course, there's a big issue of what do we do with it in the end. I mean, how we actually turn it into something which we can measure. I'm not going to talk about it now. Anyway, that's where I want to stop now. This is let's take 10 minutes break. Continue at 11:05. Okay, for those of you who were a bit worried, not all the course is going to be that philosophical. But I do think that, especially after you already know the mathematics, it's actually good to think a little bit about the foundations. And those of you who don't like it, I apologize. Now, so what are these two axioms, or these two rules for the probabilities? I mean, okay, so essentially you all should know them. I mean, so the probability of a union of two events, what is it? Of two subsets. So again, if you're not sure, essentially what I mean intuitively is the area of the union of these two sets. Okay, so what should it be? So it should be P of A plus P of B. But obviously here we counted some area twice. I mean, so we counted the intersection twice. So we need to, if we really want to be consistent with measure theory, we need to subtract the intersection. Okay, so this is one axiom that follows again from this, one result that follows from Cox's axiom. And then what is the probability of an intersection? And of course, first of all, I can generalize it to any countable union of sets. Of course, it becomes very, very complicated. Unless what? I mean, because now I have to, if I have three sets, let's say, then the intersection of two pairs, and then the intersection of triplets, and intersection of what? It becomes a very complicated formula. Some of you may have heard it. It's called the inclusion-exclusion formula, and it's actually a nightmare. So we don't want to deal with such things. But if there is one condition where it's very simple, when? If they're all disjoint. So if I also assume that for any I and j, Ci intersection with Cj is the empty set, which means that this is what we mean by disjoint sets. זרים? אני רואה שאפשר לדבר עברית. Okay, so yes. Sorry? I different than the absolutely. Of course, cannot be true if I equals Z. Then what this will be? Simply the sum. Okay, so this is of course true for any finite sum. I 1 to n or something like this, but we can extend it to what we call countable sums, countable unions. That's about it. Beyond that, we get into trouble, so we don't want it. Okay, beyond countable. Well, what happens with intersections? So here again, we actually say that we actually defined a new notion, which you call a conditional event, which really has something deep in it. We'll talk about it why in a minute. So for example, what is the probability of A if B actually happens? So we know that B happens. We know that B is true. So we know already that we are somewhere in this set. Okay, actually I'm referring here to something much more refined, which you call sampling. Talk about it in a second. But if B is true, then the probability of A must be the relative ratio of A in B. Okay? So essentially what this means, so we define the conditional probability. And this is actually a very important extension. Without this, we can't do much. So the probability of A given B should be exactly the probability of the intersection of A and B divided by the probability of B. This will give us the relative ratio. So now we think about B as the whole set, because B is already given. So we are confined to this set. And this will be, I know it's very elementary to some of you, but it's going to be this. So this is you can think about it as a definition, but it's again inevitable. In a sense, this is the only way of defining consistently with logic the conditional event. A, what is the probability, or how likely I want to think about A given that B happens. And again, the intuition is very, very simple. Think about sets. I think about the measure of the intersection in this set. Okay, so it's nothing mysterious about it. Okay, so and from that I see immediately that P and A and B, or intersection with B, is what? It's simply the probability of A of B, if you want, times the probability of A conditioned on B. And I can reverse the argument in a symmetric way. There's nothing special about A or B. I can alternate it, so it's probability of A times the probability of B conditioned on A. Both of them simply describe this measure, this area. Okay. So this is enough to already get in trouble, because it means that we now have Bayes' rule, and we already can do things which are a bit problematic for a reason I will just say in a second. But in particular, if the probability of A conditioned on B, if P of A conditioned on B doesn't change, I mean, if the probability of A doesn't change if I know that B happened or B is true, what does it mean? It means that this remains the probability of A. Okay? So then we say that what do we say? We say that A and B are independent. In some sense, the fact that B is true doesn't change my belief or my probability that A is true. Which exactly means that. I mean, the conditional on B doesn't change. If this is true, then we say that A is independent of B. And this is a very, very important concept in probability theory. And then, and only then, we can say that the probability of the intersection or the end is simply the product of the probability. So in some sense, these are the two fundamental properties of probability calculus. Intersections of independent things go to product. So it's translated into product of the measures. And unions go to sum if there's disjoint, and here if they are independent. By the way, this is essentially a factorization into independent events. I mean, A conditioned on B is independent of B. That's precisely the meaning of this product. So I can always write it. Actually, Noga did it. I can write the probability of a long sequence of events as a product of conditionally independent things. Okay, it's called conditionally independent. In principle, that's all you need to know in order to calculate anything in probability theory. Everything else follows directly from mathematical reasoning, with some definitions that I need when I talk about random variables and when I talk about real-valued random numbers. So, and I need to extend this notion of probability of a sample space to what we call probability density functions, or PDF. Probability density are not probabilities. You can have numbers greater than 1, for example. So if you look at the Gaussian, for example, and I ask you what does it mean that the top of the Gaussian is 7? So of course you know what to do. The density function is always within an integral, or multiplied by a small interval. Otherwise, it doesn't mean anything. In order to turn it into probabilities, I must multiply it by some volume measure, which can be length or area or space or whatever. It depends where you are. Questions about it? Okay, so this was just to complete the story. And now I want to ask another question. How do I estimate probabilities? What is actually the practical meaning of all of this? In the world, I mean, okay, I want to ask you, what is the probability that it will rain tomorrow? What do I mean by that? What is the practical, or if you want, how to estimate? How do we estimate? Estimate probabilities. actually, this is what's connecting it with anything real. I mean, so far I was just playing with mathematics. Probabilities. Okay. How do I estimate probability? What is again the practical meaning of probability? Why is it interesting? Someone. So there are many interpretations. Okay. Let's start with the simple one. So the simple one has to do with a very important concept that he wants to call sampling, or actually random sampling. So what do I mean by this? Well, you all know that, no? What do I mean by random sampling? I need something new. I mean, so far I talked about measures. But how is it related to anything real? I mean, if you play bridge, I want to calculate the probability that my partner has the king of ace. Okay, what should I do? Or if I throw a die, what should I tell you? If I tell you that it has a probability of 1/6 falling on 6, what do I mean by that? Okay, good. What's your name? I want to recognize you. It's not because I'm... so if you can tell me the name, sometimes I remember. Omri, okay. You'll never know when I remember, but it's an uncertain event. So random sampling is essentially, it's again very intuitive idea that I can throw darts or something like this on this square at random. What do I mean by random? In this case, there's some mechanism that allow me to blindly put points here, such that they have the same likelihood or the same probability to be everywhere. Or in some sense, it's uniform over the square, and I can draw points at random from this square. What does it mean? Okay, practically, let's say if you write a computer program, you call a random number generator twice, two numbers between 0 and 1, one here and one here, and you get a random sample. Okay, of course I'm cheating. Well, how do I draw a random number? I mean, actually, it's a very non-intuitive question. What do I mean by that? So I don't want to get into it. I just want you to to get a little bit troubled by the question. So we really need a mechanism of randomly sampling my space. And this is fundamentally rooted in intuition behind probability. So I have this notion of random sampling. Actually, I even want something more stronger than that, independently sampling. I mean, so I can sample it many, many times independently. What I mean by independent here is that the samples don't affect each other. So the result of this sample doesn't going to affect the result of another sample. Okay? So they're independent samples. So I even want independent samples. And then I can send something very nice, okay, or something very important. So what I mean by the practical meaning of probability, so let's say when I say that this has a probability P of A, it means that if I throw many, many points here, the ratio between the number of times that I hit A and the total number of my samples should be what? Oh, okay, that's tricky. Okay, because so I take random samples, and I just let's call the number of times hitting A. I denote it just like this per second, and I divide it by. So I take n independent samples. This is if you want the number of times I was hitting A, or what sometimes you call the frequency ratio. I mean, so I hit A. Many times I will hit A, sometimes I will not hit A. Something interesting, obviously this is a random variable. Okay, what do I mean by that? Well, Noga defined a random variable very formally. It's a map from the sample space to the real numbers. Okay, so this is a real number that is taking events. So it's a random sample, which means that this can have many values. Maybe by chance I throw it 10 times and never hit A. okay? Or maybe I throw it 10 times or all the times hit A. So this number has some properties that I can only talk in terms of probability itself. But actually, there is a very important property that you all should know. So when n goes to become very large, what happens to this? So this is a special case of what we call the law of large numbers. So really, is the fundamental property of probability. So if I really want to estimate probabilities, I have to try my event many, many times and randomly sample it. So this will eventually go to the probability of A. Okay, so this is my assumption of my practical definition of probability as a ratio of frequencies. So I assume that I can randomly sample the space, and I can generate ratios like this, frequency ratios. This is something we call frequency ratio. Okay. Now, so now I ask you, okay, if this is the interpretation of probability, what do I mean by the probability that tomorrow will rain in Jerusalem? Something you hear on the news every day, or in principle. I wish they were giving you probabilities, but they could, okay? The forecast people, I mean. Okay, so what do I mean by that? I have to very simple. You just have to sample tomorrow many, many times and see how many of tomorrows will have rain and how many will not have rain. Okay, that's a very practical proposition, but obviously it's a bit difficult to execute. I mean, I cannot, at least in any word that I know, repeat tomorrow many, many times and see exactly how many of them will have. So this particular interpretation of probability as a frequency ratio is somewhat limited. I mean, it doesn't capture everything we would like to say about certainty of events. But it's very important this is true. Actually, as you all should know, this is a special case of what we call the law of large number. How is it usually formulated? I mean, you all learned probability. You know? So the law of large number, it's really the first and most important property of probability is if I have independently, if I have a random sample, a random variable, which has a probability distribution P of x. And for being able to write this without explaining it, this is precisely why I wanted Noga to explain the basic things. So when I say x has a distribution, probability distribution P of x, and then I take n identically distributed samples, which I mean x1 to xn, which means that I independently measure or draw a value out of this distribution, a real number. Okay? It's very, very important. Okay, so I have a sample of size n of independently draw values. So what will be the law of large number in this case? It will have the following form. If I average, now it's real numbers, okay? So I can sum them and average them. These are random variable. It's a random variable. So these are numbers. I can sum them. What is the meaning of the law of large number here? So this will approach in the limit, again, of large n. This is what will it approach? The expectations, yeah. So this will approach when n goes to infinity. And this is extremely important, so I want actually to prove it. The sum of all the possible value of x, p of x i xi, which is something which we denote by the expectation of x with respect to p. Expectation. So this particular statement, and I can now prove. I mean, you can prove. If this is true, why is this true? How is this property follows from this? So again, remember, what is a random variable? It's a function from my sample space to the real numbers. So I can look at all the sets for which x has a certain value. So let's say the random variable is the numbers 1 to 6 of a dice throw. So there is some sets of events which gives you 1, another set of events that gives you 2, another set of events, another set that gives you 3, and so on. They are disjoint. Okay? And now all I need to do, sampling the random variable is actually sampling these sets in the random way that I did here. And I'll get that following this, the number of times I hit each of these sets is simply going to be proportional. It's going to be n times the probability at the end of this set, which is going to be precisely the probability of the value of this random variable. So each throw here will be sampling of the sample space, but the random variable was a function from the sample space to the real numbers, which means that I can partition my sample space into regions where the random variables has a certain value. Okay, let's say 1 to 6. So there are 6 regions in this space. They may be equal probability or not. I don't care. Now I have this random sampling mechanism, and I throw my dart, if you want, into this square, and I ask how many times I will hit each of which regions, and I know that in the limit it will be exactly n times the probability of this region. So I just translate it into the probability of the value of the random number, and that's how I get this. So this is really simple. This was not a terribly formal proof, but you can all see why it's true. Okay, but this is one of our fundamental properties. This is really something we need, and we're going to use again and again and again this particular limit. Actually, we want to be much more precise about this limit. We don't only want to say that it approaches this. We want to know how fast or how close it's going to be if n is finite. And this is and there are many ways of saying things about it, and many bounds that tell us how far is this number going to be from the expectation for any finite n. So we're going to be much better quantified using bounds like the Chernoff bound or like the Chebyshev inequality or like Markov inequality. You heard about them. Essentially, so we are going to be we want to be a lot more quantitative about what do we mean by this limit. But at this point, it's enough for me to know that this is the meaning of sampling. So again, it's not enough to have probabilities only interpreted as ratio of frequencies, or ratio of frequencies, frequency ratios, because we really want something more than that. We want to be able to talk about the probabilities of events that we cannot sample many times. Actually, Bayes' rule, which is a trivial consequence of the definition of conditional probability, is already allowing us to ask questions about things which we cannot sample from things that we can sample, and we calculate those things. I mean, what is the probability that it will rain tomorrow? I can turn it into another probability. We'll get to this in a second. And actually deduce it using calculus of probabilities from things that we can sample. Okay, and here, by the way, already there's a big split in the statistical community, at least. Some people believe that you shouldn't talk about events that you cannot interpret their probability as the ratio of frequencies. These people are called the frequencists, and it's kind of religion. I mean, they don't. It's really, to me, it doesn't make any sense because they're really limiting themselves. But some people really want to be able to always interpret in terms of ratio of frequencies. Other people, like me, want to think about slightly more general think of the meaning of probability as really a measure of belief. How much I believe that this will happen. When I say that it's going to be 60% or 0.6 probability to rain tomorrow, of course I have to define it more carefully what I mean rain tomorrow. Where? What time tomorrow? What part of the day tomorrow? It can be many things. But once I define it properly, I actually want to be able to say it's 60% probability of rain tomorrow, and you'll know what I mean. And you'll be able to verify it. What I mean by that. Okay, so we actually want to extend the notion of logic not through frequency ratios, but as a measure of belief. In order to be able to calculate expectations, even over things that we don't really know very well, or can't really sample. actually it's getting even more hairy and hard to interpret when you talk about quantum mechanics, but I'm not going to get into it. So those of you who heard about it know that the whole notion of connecting these amplitudes with measurements is a big headache which is still not settled. Actually, some of the old interpretations of quantum mechanics, like the Copenhagen interpretation, are probably completely wrong from what we know today about the world. So, and this is just for the physicists again. Anyway, so we go back to real things. So the first topic that we really want to teach here is an application of information theory, of probability calculus to a very practical question. How do we make decisions? So I want to talk about decision, what we call statistical decision theory or probabilistic decision theory, and for that I want to erase some of those things. Now that this part of the board is essentially useless. So this one. Okay, so a new topic, or if you want the first chapter or the second chapter of this book, is what we call statistical decision theory, or just to be short, SDT. And so what do I want to formally, this may be for some of you the first time we formally see some use of probability theory. I want to formulate the intuition behind decision making. Or not, we're going to make something very, what we call simple decisions, something like the canonical example that every textbook and every lecture is using. I said something about the probability of rain tomorrow. I want to decide if to take an umbrella or not. Okay? I know this is a boring example, but it's still very useful. So I wake up in the morning. How do I decide if to take an umbrella or not? How do you decide? What is the process that you're going through? Okay, maybe some volunteer. Yeah. Looking outside. Good. Okay, so you look outside, especially in Israel, that's very useful. You look outside the window, and then what? You see if it's cloudy or sunny. Okay. You look at your phone, and you listen to the radio, and then do many other things. I don't know what. But essentially, all those things that you do, that's precisely what you do. Something which we can call observations. Okay. We actually look at something which may depend on the world. Okay. So we again want to formulate it in a minute. And these observations should, of course, depend somehow, if they're useful. I mean, if I just look at the phase of the moon, for example, it's probably not going to tell me much about the weather here tomorrow. Maybe, I don't know. But if I look, I don't know what. There are many things that are not useful. But if it's useful, then there should be some dependency between this observation and the fact, or the state, what we call the state of the world, which means, is it going to rain or not? Or is it raining or not? There's a delicate issue of future and present and past here. But let's say that I'm talking about now. I mean, during the day as one event that I care about, no time. So, so what do I have? And then what? Okay, you look. How do you make the decision? What's your name? Karen. Okay. Go on. I mean, you started, you have to complete it. How do you make the decision? Based on past experience. Okay. Okay, very good. So essentially, just tell us, look, we know something. That in Jerusalem, in November, there are clouds. There is such a belief. Of course, I cannot be certain, especially in Israel, you can almost be certain it will not rain, but sometimes they are wrong. So actually, the last few days were quite surprising in that sense. So you have what we call prior knowledge or prior belief, okay, which we would like to formulate in terms of probabilities about the state of the world before you saw the observation. And now you see the observation, and you want to update your belief, and then decide. Well, actually, it's a very complicated process. I mean, you observe, you combine it with some sort of probabilistic structure of your beliefs about the world, and then you make something completely non-trivial. You make a decision. I mean, you decide to take an umbrella or not. You cannot take half an umbrella. Maybe you can, right? Most of us can't. Or you can't take an umbrella with some probability. Maybe you can, right? I mean, you can take, decide that there's a random choice you have to make, and you throw a die and decide, okay, I take an umbrella with probability 0.6. Sometimes you take something. It's also a possibility, by the way. It's not necessarily wrong. But, yes. It's a good question. Let me try to be a little bit more formal. So I want to do it very quickly because I have exactly 10 minutes. It's really very simple. Actually, I'm continuing tomorrow for those of you worried. We have 4 hours. So we have, what are the elements that we encounter in this process of making a decision? So we have something we call observations. And we have something we call the state of the world. Which in this case is rain or not rain, something like this. It can be much more complicated, of course, and we're going to extend it to many states, countable states, incountable states, whatever, it can be many things. State of the world, observations, and what else? So was something which I call the action. No, okay, good point. We actually don't observe the state of the world. I mean, you observe if there are clouds in the sky. No, the state of the world is it going to rain or not. So this is something I really want to know, but I can't observe it directly. I have what we call partially observed world. I have something which depends on the state of the world, but it's not the state of the world. Or you look at your phone, which is even further away from the state of the world. I mean, I don't know, maybe better observation, but you don't observe the state of the world. If you observe the state of the world, fine. Then it's a fully observable world, and we are in good shape. Usually we are not. We are only in what we call partially observable world. We don't really see the world. We see only some functions of it, and this function is what we call stochastic. I mean, it's random. It's a random variable that depends on the state of the world. Okay, we'll make it explicit in a second. What are the other elements here? I just want to make sure. So there are actions. Actions, in this case, so this was a sky. I don't know, clouds, no clouds, whatever. This was rain or rain. Okay. This, what are the actions here? Take umbrella or not take umbrella. So binary action. Maybe the actions are more complicated. I mean, you want a raincoat and umbrella, or you want something, I don't know. There can be complicated structure of actions, but these are the things that we actually do. Okay, that's what we have to decide on. Okay, so these are, and there's another interesting aspect, which I didn't mention so far, and it's very important, is what is the cost, or what is the price of making a decision in a given state. So let's say, if I don't take an umbrella and it rains, okay, how much I'm willing to suffer? I mean, it's in some sense, okay, I'm going to get wet, maybe. So how bad is it? Or if I carry an umbrella and it's not raining, how much does this cost me? I mean, okay, so usually we quantify our decisions with some sort of a cost. Or okay, so let's just be a little even more formal. Let's call the observation X. It can be a vector of things. Let's call the state of the world W for world. You can also call it omega for other things, but W. The state of it's a random variable. This is a random variable. This is a random variable. Because I don't know what they are. They're random variables. They're not necessarily even real numbers, but I think about them as random. Okay, and the actions, let's call them alpha or A. So this belongs to the set of take an umbrella, take, not take. whatever we take. For example, umbrella is a hard word. So it's clear what I mean by this. So we have three variables here. Alpha, which can also be a complex action. I mean, many things. The world is some random variable, and x is some random variable. And then we have prices or costs. So this is a real number, usually. That's at least the way I want to think about it. It's a utility function, or it's a value function, or it's a cost function. These are all more or less the same things, which should be a function of what? It's a function of my action and the state of the world. Okay? So what is the cost of taking an umbrella and it's not raining? Or what is the cost of not taking an umbrella, of taking an umbrella and it's raining? Maybe it's also a cost. I mean, I don't know. So we usually write this cost as a lambda, just a notation that is common. And it's a function of alpha, my action, and what I said, the state of the world. Actually, I usually like to write it like this. It's conditioned on the state of the world, just like I like conditional probabilities. So what is the cost of taking an umbrella when it's raining, at the state rain? What is the cost of not taking an umbrella when it's not raining? So this is a function from what? From A cross omega into the real numbers. Okay? It's a function of these two variables. So this is the cost. So this is some sort of a matrix. If the number of alphas is finite, in this case, rain, no rain, take, not take, this is a 2 by 2 matrix. Okay? So far, these are the quantifiers which have nothing to do with probabilities, but we also want our probabilistic model. So what is this? So Karen told us something about prior beliefs or something like this. Maybe he didn't use this word, but that's what I understood from it. So you said something about how much you know from experience or whatever. So in this case, let's say it's the 4th of November, Jerusalem. What do I know about the probability of rain in Jerusalem on 4th of November? This is a very general knowledge. I can look at the average over many, many 4th of Novembers. This is getting close to repeating the day many, many times. So essentially, I can really look at, okay, let's say that everything else is averaged. There are many, many other things that affect the weather 4th of November, but we average over them, and we have a probability, a prior probability of a state of the world, which you call the prior probability. It's a very important, here we actually make an assumption that we can estimate this prior, that we know this prior. What is the probability of rain in Jerusalem on the 4th of November? Okay. Once we do this, we already put ourselves in a group of people that call themselves Bayesians, but which are not frequencies, but we're Bayesians, generally speaking, in this course. Yeah. Okay. Not yet. Momentum. This is just what she called prior knowledge. Before I see anything. Okay? You're right. There's something correct in your question, but so what's your name? Omri. Okay, that's about my capacity. Was listening for one lesson. So there is something else which is really this. Okay. How are the observations connected to the state of the world? Or in other words, in this example, what is the probability that it will rain? It will be cloudy at 7 in the morning, and it will rain during the day. So given that it's going to rain, what's the probability of clouds in the morning? Or given that it's going to rain, what's the probability of sun in the morning? Given that it's not going to rain, what's the probability of clouds in the morning? Given that it's not going to rain, what's the probability of sun in the morning, or something like this. Okay? So it's a very simple and very intuitive type of game. So we have these two. And now we can start calculating things. I want to make a decision. So what do I mean by making a decision? I want to choose my action given my observation. Okay? Now, I don't know what the state of the world is. I know that it was cloudy at 7 in the morning, and I want now to make a decision, take or not take the umbrella. So what is... Yeah, the prior knowledge is going to play a role in a second, but first of all, there's something which I sometimes call strategy, or policy, or decision function, or something like this. And this is, in principle, is something that's supposed to tell me what to do when I see clouds in the morning on the 4th of November. The clouds, the prior knowledge is going to affect my decision. So the point is really how to calculate. So in Amir's notation, we call this policy a function of the observation, which is, so this is if I assume deterministic policy. So this is going to be a map from the observations, this random variable x. So I'll try to be consistent with it. X, big X denotes the random variable, small x denotes the value, a sample of this random variable, a certain value. So it's a function from x to what? To a. Okay. This is if I'm thinking about what's called deterministic strategy. I mean,